Good evening, everyone. It's really good to be back with you. Good news, we're going to wrap up Chapter 4 tonight, and that will be a milestone for you, for sure. Just like to make a comment, if we've got YouTube, people finding us on YouTube and watching, if you're doing it while the class is running, please contact Gary and we'll get you on the mailing list so that you can get the advance notices of what's going on. But if you miss that, everything is stored on the YouTube pages as well. Just ask us if you have any questions. And the email list is only active while the class is running. All right, so Chapter 4, Part 2. This is a little less challenging than last week, which will cause some of you to breathe a sigh of relief. Last week we did cover some things that were a little involved, but that's okay. Hopefully you've been practicing and reviewing to make it your own. We're going to have some easy stuff tonight too, which is welcome news. And as always, there's a lot more in the book than what you actually need for passing the test, for answering all of the pool questions. So we're going to just be focusing on what you need tonight, as we do every week. So we'll be going through the problems, the math problems that are in this part of the book using the calculator tonight, but I did rewrite a document that I included in the handouts that I sent out last Thursday that will give you a path to passing your exam if you're stuck in a situation where you're doing an online exam and they won't let you use any calculator except the one on your computer. So I'll probably have more comments about that later, but it is possible to do it that way. That is a brand new document, so that'll give you another way to get through this if you feel like you're going to be stuck there. All right, just like to remind everybody to go ahead and get your tests scheduled if you can for December. And tonight we're going to finish the Chapter 4, and then I've got some real interesting demo stuff that we'll be doing at the end if we have time, and I think that we will. So this is what we're covering in this part of the chapter. Plow right into it. There's a handout that I sent on Thursday. It was actually 2 pages, 2 copies on each one, that I call a formula review. And if you have that, if you printed it out, I would urge you to get that out and have it handy tonight, because what I'm going to recommend is that you write these formulas in as we touch on each of them tonight, and then on your own time take a blank copy and see if you can reproduce this sheet from memory. In fact, I've got a bit of a challenge. If you can write all of these in 1 minute or less and do it on your own without looking, you're going to be well on the way to being able to do all of this using the calculator method. So if you've got this, get it out. We'll be doing it. I'll go over to the calculator cam for a second. And we've got the blank sheet here. And then this will be what it looks like when you've got it filled out. So go ahead and complete yours as we go through our presentation this evening. This is all on the extra class reference sheet as well. Just trying to give you some learning aids and helps along the way. And as I said, the memorization challenge, try to do this from memory in no more than 1 minute. You really don't own this, so to speak, until you can do it on your own. Okay, one more bit of preliminary information here. Memory trick for reactance. We've talked about reactance quite a bit last week. So the symbol for a capacitor is here. You can let the circuit symbol remind you of the formula. X sub c equals 1 over 2 pi frequency c. This kind of represents the over part. And you can also let the circuit symbol remind you that reactance and phase angle will be negative for capacitors. So if that's a mental trick or help that will be beneficial to you, that would be wonderful. And then inductors are just the inverse. X sub L equals 2 pi frequency L. So if you've got your formula review sheet handy. You can go ahead and write these down on your paper right now. X sub c equals 1 over 2 pi frequency c. X sub L equals 2 pi frequency L. And if you don't get that right at this exact moment in time, these are on your extra class reference sheet as well. Okay, now we're going to get into resonant circuits. This is really magical stuff. And ham radio, we wouldn't have radio if it wasn't for this. This will tie some of the things together that we talked about last week. And it's really good stuff. So first of all, we're going to talk about magic at resonance. We talked about the resistive and reactive axes last week. And here we plotted some value of inductive reactance, again positive. And we're going to add some capacitive reactance. And something magic happens here. If these are the same, the poof happens. You can almost hear it and see the smoke rising. So what happens is X sub L and X sub C cancel entirely, leaving you with only resistance. That happens at the magic point of resonance when capacitive and inductive reactance are equal. All kinds of things come from that. There's one related pool question. At resonance, voltage and current are in phase. Because we've canceled out any reactive components, that only leaves resistance, and so voltage and current will be in phase. Get into it a bit more. The magic of resonance happens when X sub L equals X sub C. And here's the formula. When X sub L equals X sub C, we saw the poof on the previous slide. We can actually solve these two. If X sub L is equals X sub C, we can solve it for resonant frequency using some algebra, which we don't have to. I'm just going to say let's memorize this formula: 1 over 2 pi times the square root of LC. And that's also on your formula sheet. So go ahead and write that down if you have that in front of you. And it happens here. Kind of an interesting story. When I was taking my extra exam, I forgot this formula, but I knew that it was X sub L equals X sub C. So using my impressive algebraic skills, I tried to derive the formula for resonant frequency. And it turned out my impressive skills weren't as impressive as I thought, and I couldn't figure it out. So after about 10 minutes, I finally remembered the formula, and I got it right. So best to memorize the formula. Now, there's nothing in this formula that makes reference to resistance. You may recall that capacitive reactance, inductive reactance operate by storing energy in the part and then giving it back. Well, resistors don't store any energy, so they don't affect this formula at all. The two problems that we'll have for calculating resonant frequency will have a resistance value, but you'll just ignore that when you get to it. So let's try to work a problem. We worked a problem earlier on. I think it was during week 2. We'll try to work another one since there's 2 in the pool. This is the one that we didn't work so far. So we'll come back over to the calculator cam and see if we can get through this one. Get everything lined up here so you can see it, hopefully. All right, so what are we going to do? Well, we need to turn the calculator on. That's what the ON button is for. And this is our formula. Frequency of resonance equals 1 over 2 pi times the square root of LC. We'll go ahead and try and do that. This is in the form of a fraction. So we'll use the box over box button right here. And in the upper part, or the numerator, we'll put in the number 1. And then using the navigation diamond, we'll go down 1 to get to the denominator. We'll see that's flashing. And now we need to put in 2 pi times the square root of LC. So 2 pi, it's the 2 key and the pi key. And then to get the radical sign in for the square root, that's the blue text right above the x squared key. So we press second to apply the blue text, and then press x squared, and we get the radical sign in there. And you'll notice that what's on the calculator is exactly matching what we're seeing here in the formula. That's one of the things I love about this calculator. All right, so L times C. L is 50 microhenries. And you may remember that micro means times 10 to the minus 6th. So we'll put that in first, 50, 5, 0. Then the exponent entry, EE key, and it's minus 6. So we have to use the negation key, not the minus key. The negation key, put in 6. So we've got 50 microhenries inserted. And then we need to multiply it times the capacitance, which is 10 picofarads. So we'll hit the multiply key up here and put in the value of the capacitor, which is 10, exponent entry, and picofarads is times 10 to the minus 12, the negation key, 12, and then I'll hold my breath and press enter. And we did get 7.12 E6, which is 7.12 megahertz. So hopefully you were able to follow along with that. I tried to go slowly enough so that if you didn't get it, you can go back and look at the video again and be successful in getting this. But that's the process. I'll be showing you 2 other ways to get at the answer as well. We like to show it on the calculator because there's a great satisfaction in being able to do it for real, if you want to put it that way. I'll also be sharing 2 other tips for getting these. We'll move on. Now we're going to talk about series and parallel resonant circuits. So we have one diagrammed here. We've got a signal generator that's putting out radio frequency energy. We've got a resistor in series with an inductor or coil in series with a capacitor. And then we have an ammeter here that's telling us how much current is flowing through the circuit. So at the frequency of resonance, X sub L equals X sub C, and they cancel. And then we've said that about 6 times so far, but that's what's behind resonance. It's a really important concept. Another thing to be aware of, and we've shared this in the past, what's happening is that the current through the inductor is going to be generating a magnetic field around it. The current through the capacitor is going to be generating an electrostatic field. So the concept of reactance is these components are storing energy and then they're going to give it back. And we'll see how that works, how it impacts us. So in this case, because they're telling us that we're at resonance, the inductive and capacitive reactance happen to be the same value, so the circuit is purely resistive. These components don't play in at resonance. Now let's see if we can decode this one in the context of the pull. The phase relationship between the current through and the voltage across a series resonant circuit at resonance, the voltage and current are in phase. That has an implication, which is here, the magnitude of the impedance, in other words, what the signal generator is seeing in an RLC circuit at resonance is approximately equal to the circuit resistance. So if the generator is only seeing the resistor, that means something pretty special. And we'll see that in the next slide. But if you can just imagine this for a second, it's the same as taking a piece of wire from the top of the inductor to the bottom of the capacitor, basically shorting out these 2 components, leaving only the resistor that's seen by the generator. We also see that the current is going to be at a maximum at this point as well. As we move off resonance to one side or the other, this no longer becomes a short, and we don't get the maximum current. So hopefully that will help these make a little bit more sense. Again, the phase relationship between the current through and the voltage across a series resonant circuit, so these parts here, voltage and current are in phase. Now the voltage and current being in phase is really referring to the resistor, because it's the only thing that the generator can see, and of course a resistor has no phase shift. And the magnitude of the impedance in an RLC circuit at resonance is approximately equal to the circuit resistance. And we're going to see that this same statement is also true of a parallel circuit, but I'm getting ahead of us a little bit. So at resonance, as we said, the inductor and capacitor basically become a short circuit. So if we put a piece of wire from the top of the inductor to the bottom of the capacitor, that's what happens at resonance. And we've had a student in the past ask, well, if they become a short circuit, why don't we just put a piece of wire there and save the cost of the parts? Well, we're going to talk about that. All right, inductor and capacitor, low impedance, they become a short, essentially. And the reason why this is important, I've added some frequencies here. So we've picked some frequencies in the 80 meter band, 3.5 megahertz, 3.6, 3.7. So you can see at 3.6, we're going to be passing the signal in a maximum sort of way. But as we tune below or above, now we're introducing the concept of selectivity, where you can tune one frequency that you want to hear, and the frequency that you're wanting to hear, you don't want to hear the frequencies on either side of it. So that's the reason why this is important, and why we don't put a piece of wire there. Because if we had a piece of wire there, they'd all be heard equally well. So maximum circuit current is at the resonant frequency. We see that in this graph here. And this is an interesting concept. The voltages across the inductor and capacitor may build as several times the source voltage. So if we've got 10 volts coming out of the generator, and we put a voltmeter across the inductor, we might see 30 or 40 volts. Well, what kind of craziness is that? And the same thing for the capacitor. Because they're exchanging energy back and forth between each other, that's what causes those voltages to build up. And stated in the terms of a pool question, resonance can cause voltages across reactive components to be higher than the voltage applied to them. That's kind of a mind bender, but it's absolutely true. And there's a principle here that our radio designers have to take into account. They can't pick value. Again, we've got 10 volts of RF coming out here, but they have to size these components to account for the voltage that's actually going to be appearing across them. But ICOM and Yaesu and all of those folks take that into account for us. Now we're switching from series to parallel circuits, and the first thing you might notice, well, a couple of things. The circuit's been rearranged differently. Instead of series components, everything is in parallel. Secondly, this graph that we saw of current through the circuit is inverted. So at resonance, the current is going to be at a minimum at resonance, rising on either side. Well, you might be wondering why would you want one versus the other? Well, maybe you want to notch out a frequency. So that would be an example here, where you can see it's being nulled at the resonant frequency. So there's some things that are very similar. At resonance, X sub L and X sub C cancel, they're equal. The circuit is purely resistive. That sounds just like we talked about before, but for a different reason. So if the circuit is purely resistive, what do you think has to happen over here? Well, these parts have to disappear. How does that work? So the magnitude of the impedance in an RLC parallel circuit at resonance is approximately equal to the circuit resistance. Well, that should sound familiar, because it's the same thing we said about the series circuit, series resonant circuit. But it's happening for different reasons. In the series circuit, the parts short out and just leave the resistor. In the parallel case, these parts disappear from the point of view of the signal generator and leave just the value of the resistor. So at resonance, we're continuing with parallel. The energy being exchanged between the inductor and capacitor will result in a large circulating current. So what's happening is the inductor is being charged, the magnetic field is being built up, and then when the phase reverses, we get to the other part of the AC cycle out of the generator, what's going to be happening is this part's going to be discharging its energy into its neighbor. So the coil will be building up a value of energy, and it will be dumping it into the capacitor, and then when the waveform changes again, the opposite's going to happen. The capacitor is going to dump its energy into the coil. So we've got this thing called a circulating current, as these two ping-pong back and forth between each other. So this results in a large circulating current, and the currents can become quite high. In fact, they can become so high that solder on a circuit board would be melted. So our radio manufacturers have to take this into account as well. Again, with only 10 volts, which we're using as our example, out of the generator, there can be massively high currents generated in this loop right here. The magnitude of the circulating current within the components of a parallel LC circuit at resonance is at a maximum. So when we're at the point of resonance, X sub C equals X sub L, we're going to have the maximum circulating current going on, which is what the pool is going to ask us. So the inductor and capacitor, this part of the circuit, have to become a high impedance. They have to basically become an open. We saw the short circuit condition across the inductive and capacitive reactances in the series case. In this case, they become essentially infinite, or high impedance. They disappear. Isn't this magical? It's really amazing how this works, and so much of radio depends on this. The magnitude of the current at the input of a parallel RLC circuit at resonance is at a minimum. That's what this graph is showing us. It's just flipped from the series case. Again, this would be the idea of maybe a notch filter. We saw perhaps the case of being able to select one frequency over another in the series case, just as practical applications of this. So we've got the concept of storing and giving back energy. I don't know why this occurred to me, but just today, a mechanical model came to mind. I started researching it a little bit, and here we've got our circuit again. These parts are storing energy and giving it back. And there's a physical model that I think applies to this really well called Newton's cradle. And I'm going to show that to you. Click this animation. All right, hopefully that's going out. Is that going out, Gary?
Yes.
Okay, so see what's happening here? The one ball is hitting the other ones and then transferring its energy to the one on the end, and it's bouncing. So this is kind of a picture of a coil discharging its energy and giving it to the capacitor. The capacitor then swings back and gives its energy to the inductor. So I thought that this was a pretty cool model. You notice that the balls in the middle don't move at all. So that's kind of like the short circuit that we see in the one case, or the open circuit in the other. So I thought that this was a really cool animation. And there's an article, this was from Wikipedia. So there's an article here that goes into that in much more detail if you're interested. But remember, we had the model of flywheel and air tank being filled in our discussion last week as physical models for how capacitive and reactant and capacitive and inductive reactance work. And here's a model for how resonance works. Now, what are some of the applications? Well, in radio, they're just almost unlimited. We see applications for resonant circuits every place. We talked about selectivity, separating different frequencies. And here we've got a picture of Gary's favorite radio, the ICOM 7660, right? Is that it? 7760. I don't have one, so I don't have it memorized yet. But here we see that we've got the lower end of the band on 40 meters, and these are our signals that are on the band. We might want to hear this one, but we don't want to hear any of these other things. So that's the concept of selectivity. So you might remember Gary's mixer math, where we have two inputs coming into a mixer. We've got the input from the antenna, we've got a local oscillator, and then we've got the sum and difference frequencies coming out of the mixer. Well, resonant circuits are what are used to pick out the one particular signal of interest coming out of the mixer. So that's another application. We want to maximize the transmit signal at the desired frequency. So that's what some of the knobs are for on the older radios. Filters, every place. We've got audio filters, RF filters, just resonant, the concept of resonant circuits works there. Of course, some of those things can be simulated in software with the software-defined radios, but in this case, we're just looking at the coils and capacitors. Antennas as tuned circuits. Well, an antenna acts very much like a tuned circuit. Multi-band antennas with traps. You've seen antennas that will work on 20, 15, and 10 meters with traps installed on the antenna elements. That all works on the principle of resonant frequencies, and of course antenna tuners. So the applications are everywhere for this. Harmonic suppression and notch filters we talked about as well. All right, and jumping right into some pool questions here. Feel free to unmute, give us a 3-second pause if you would, and share your answer. What can cause the voltage across reactances in a series RLC circuit to be higher than the voltage applied to the entire circuit?
Delta?
Alpha.
Alpha, it is alpha, resonance, yeah.
Yeah.
All right, very good. And don't feel bad if you get an answer wrong, because that'll help reinforce it for you the next time you see it. So
You'll remember.
You'll remember, yeah. Same thing with doing the self-tests at the ARRL site. Don't despair over a wrong answer. Just ask yourself, why did I get it wrong? And you won't get it wrong the next time. It's a learning technique. What is the magnitude of the impedance of a series RLC circuit at resonance? If you can remember the shapes of the graphs, that would help. Although the shapes of the graphs won't actually answer this question for you.
Delta.
Delta, yeah, approximately equal to circuit resistance. Now they're asking about the impedance of a series RLC circuit. If they were asking about the impedance of a parallel circuit, it would be exactly the same answer. That might even be the next question. Ah, look at this. What is the magnitude of the impedance of a parallel RLC circuit at resonance?
Alpha.
Alpha, yep, for a different reason. In one case, the parts are shorted out in the series case, or they disappear entirely in the parallel case, making this statement true for both types of circuit. What is the magnitude of the circulating current within the components of a parallel LC circuit at resonance?
Bravo.
Bravo.
It is bravo. It's at a maximum. So right at resonance, those the parallel inductor and capacitor are just beating each other's brains out. It's kind of like playing ping pong, or the model that I showed you, the mechanical model. What is the magnitude of the current at the input of a parallel RLC circuit at resonance?
Alpha.
It is alpha, and here's where thinking of the shape of the graph would help you. What is the phase relationship between the current through and the voltage across a series resonant circuit at resonance? There's some that are going to be tempting.
Charlie?
Charlie.
It is Charlie. Voltage and current are in phase. Some people will want to look at these and say, oh, I remember that, but that's just for the part by itself, not at resonance. So that's why C is correct. What is the resonant frequency of an RLC circuit if R is 22 ohms, L is 50 microhenries, and C is 40 picofarads? Well, two ways you can approach it. There's really three ways to get to an answer. The formula that we shared, and we're not going to work through that again. So that's one way to get to it, and I encourage everybody to at least try that and make sure that you can do it, because it could come in handy in your future ham radio endeavors. That's one way. Okay, the second way to answer this question, since you're all probably general class hams now, you're probably aware of some of the bands. So the two resonant frequency problems in the pool, the answer comes out to be in a ham band. And if you look at these answers, there's only one that is in a ham band. That's this answer, C, 3.56 megahertz. So now you have two ways to answer the two resonant frequency problems. I'll give you one more. If you can't remember any of that, then the next trick will get you there. Pick the answer that's closest to 5 megahertz. Okay? So if you do that, that turns out to be C. So the three ways you can get to this, and two of them don't involve calculating it. So you're welcome. So it is C. And here's the other one. Same discussion applies. Same three ways. And there is one way they try to trap you here, and that's there's a kilohertz answer and a megahertz answer. Well, so delta is the only one that's in a ham band. It's also closest to 5 megahertz. So that will get you there if you don't want to or don't remember how to calculate it. All right, we're through those. Those are probably the most complicated ones that we'll look at tonight. The other calculation problems are really quite simple. So Q. Do we have any Star Trek fans amongst us? You can just wave if you're a Star Trek fan. Okay, yeah, you might remember Q. Well, this has nothing to do with the Q in Star Trek. And kind of think of Q as standing for quality, and it has the idea of selectivity or sharpness of tuning. Q and quality factor go together, and we'll see how those develop. So we've got practical and ideal circuits to think about. So practical components, here's an inductor, and it has leads on it. It's got wire leads on it. And those wire leads are going to have some amount of resistance, probably very small, but it exists nonetheless. Same thing with capacitors. Capacitors will usually have leads, wire leads on them, and we've got some value of capacitance. So practical components can be represented as ideal components, perfect capacitance, perfect inductance, in series with a resistor, usually representing the leads of the resistor. In the case of a coil, because a coil is wound with wire, the wire that the coil is wound with is going to have some resistance. Now the resistance dissipates some of the stored energy in that ideal component, or waters it down. Another way to look at it. So the quality factor of a component is basically the ratio of the reactance to the resistance. It represents how close an ideal component the practical component actually is. And again, ratio of how much energy is stored to how much energy is dissipated in these cases. Now the only way to increase the Q of an inductor or capacitor is by using components with lower losses. How would we do that? Well, in the case of a coil, you've seen large, they're actually tubing that's wound around. Sometimes they'll silver plate a coil to lower its resistance. So those are examples, and there's a price to be paid here to getting closer to the ideal makes the part more expensive. So increasing the Q in a series resonance circuit will cause internal voltages to increase. Okay, where if you remember the case of the series resonance circuit, that's kind of related to this. If we're not washing out as much of the reactance by having less resistance, that increases the Q, which will cause the internal voltages to increase. So any resistance that exists in the parts will basically water down the purity of that reactance and lower the Q. Increasing the Q will cause internal voltages to go the other way, to increase. Now let's talk about why some of this is practical. Let's look at this diagram first of all, and we're going to talk about bandwidth. The concept of bandwidth is the range of frequencies that can be passed by this either filter or resonant circuit in our case. And there's a concept here called, well, Q and bandwidth. We're going to talk about how they're related. So the way that this is defined, so if we're passing a signal right down the middle, and then we're going to move the frequency either above or below the point of resonance, at some point the signal that gets through is going to be reduced by half. Half in terms of dB is 3 dB. If we take a signal and reduce it by 3 dB, we're going to cut it in half. And that's what's defined as the bandwidth. It's the distance from being right on frequency resonance to the point below or above where you're only getting half of the signal. So let's see if we can relate that to what's being said over here now. Bandwidth is the frequency range where the voltage or current is no more than 3 dB below the peak. Okay, and we kind of explained that. Also called the half power or minus 3 dB bandwidth. And you might be looking at this diagram and saying, well, why wouldn't I want the narrowest possible selectivity? Why would I want anything wider than that? Well, consider the case of single sideband. Single sideband is approximately 3 kilohertz wide. So you would want to be able to pass 3 kilohertz. If you're running CW, you might only want to pass 150 hertz. So a Q that's higher in that case would be preferable. So you can see that as Q changes, a high Q will give you narrower bandwidth. A lower Q will give you a wider bandwidth. Inverse relationship there. So that's a practical example of why you might want one versus another. Now the formula, this is super simple. I think there's 2 questions like this. Half power bandwidth, that's going to be the distance between this point and this point, the 3 dB points above and below the resonant frequency. Okay, frequency of resonance is the FR, and Q is the circuit Q. So if that sounds complicated, you'll see when we go to calculate one of these, it's not complicated at all. So a higher Q narrows the bandwidth or makes the circuit sharper. We saw for the CW case, I'm just throwing out these numbers. They probably don't work out exactly as I'm describing, but just follow my reasoning here. Q of 100 might be for the 150 hertz bandwidth, narrow. The Q of 10 may be for the single sideband. So we'd want different filters for the different modes that we're receiving. So higher Q narrows the bandwidth. Increasing the Q, and I'm hoping that these words will make sense now, increasing the Q of an impedance matching circuit will decrease the matching bandwidth. Okay? So let's see if that fits with what we've talked about here. So if we increase the Q from 10, like for single sideband, to the Q of 100, for, let's say, CW, increasing the Q of an impedance matching circuit will decrease the matching bandwidth. Well, in our example, that turned out to be true. We raised the Q from 10 to 100 to get this from 3.5 kilohertz to 150 hertz. So you think about that for a second. The term matching bandwidth shows up in a couple of pool questions. Again, the bandwidth is the distance above and below the resonant frequency where the signal is reduced by 3 dB. Determining Q for a series resonant circuit, that's the only one we're going to look at. There's a parallel case as well, but we're only going to look at the series because that's the only one that has a pool question in it. Determining Q for a series resonant circuit is the bandwidth of the circuit's frequency response. And again, with all of this explanation, I'm hoping these words will make some sense. You know, why the right answer is the right answer. Determining the Q for a series resonant circuit is the bandwidth of the circuit's frequency response. They word it kind of funny, but if you kind of think through the words, I hope it'll click. So how do we calculate circuit Q? That's the next question. So we're only going to worry about the case of a, well, we're going to actually talk about both of them. The Q for a parallel resonant circuit is this formula. It's a reactance, or resistance over reactance, R over X. And we had a fellow that was helping us with these classes, Tom Walton. Was a paramedic, so he was always thinking of medical shortcuts or analogies. So in the case of parallel, P, prescription, is an Rx. So if you can remember that, you'll know how this formula works. P, Q for a parallel circuit, is an Rx, R over X. The Q of a parallel resonant circuit is the resistance, R, divided by the reactance, X, of either the inductance or capacitance. Now, why do you suppose they're saying that it could be either the inductance or the capacitance? Anybody have a thought there? Not hearing anything, but remember at resonance, the inductive capacitance, capacitive reactance and the inductive reactance are equal, right? So that's why you can apply this formula using either the inductance or the capacitance, because at resonance they're equal. So again, the Q of an RLC parallel resonant circuit is the resistance divided by the reactance. So if we're given the resistance and the reactance, we can easily calculate it. All right, now we're going to go work a really difficult problem. And I'm just kidding, this is a really easy problem. So back to the calculator cam. So half power bandwidth is the frequency of resonance divided by the Q. Another way that I'll give you a shortcut, it turns out to be the big number divided by the smaller number in both the cases where they ask a question. Now by big number, you might say, well, 7.1 is less than 150, but it's megahertz. 7,100,000 cycles per second, hertz. All right, so let's see how that works. I'm going to clear calculator. And it's just the frequency divided by the Q. All right, so let's work that out. So this is in the form of a fraction. So we'll use the box over box key. And then the top one, we're going to put in 7.1 megahertz. That's going to be 7.1 EE for exponent entry. And megahertz is times 10 to the positive 6th. So we don't have to worry about this negation key or anything. EE6, okay? So we got our 7.1 megahertz entered. Now we'll use the navigation diamond, press down to get to the denominator. Q is 150, 150. And press the enter key, and we get 47.33 E3, which is 47.33 kilohertz. So this might look a little complicated, but it's super, super easy. It's the megahertz divided by the Q. All right, so and if you don't have this written on your formula review sheet, you can certainly add it now. Half power bandwidth equals FR over Q, frequency of resonance over Q. And we're right to some pool questions. Which of the following can be used to determine the Q of a series-tuned circuit? You have to remember some of the words we spouted off at you.
Alpha.
No, that's where you might have got that confused with the half-power bandwidth. It's actually Charlie, the bandwidth of the circuit's frequency response. So we're looking at how many frequencies are being passed from the low end to the high end to get down to the 3 dB point. So in the very middle, we're passing the maximum signal. And then as we tune down, we get to the half-power point. Okay, and then as we tune up, we get to the other half-power point, and the distance between the two is the bandwidth of the circuit's frequency response. So with that, and this is worded kind of in a difficult way, but just think of it again. Which of the following can be used to determine the Q of a series-tuned circuit? Well, it's the bandwidth of the circuit's frequency response, if you can picture that graph in your mind. What is the result of increasing the Q of an impedance matching circuit? Remember, if we increase the Q, we're going to be decreasing something else.
A alpha.
A alpha, right, A alpha, exactly. Matching bandwidth is decreased. Same principle applies if you can picture the graph that we shared. How is the Q of an RLC parallel resonant circuit calculated? This was our prescription again.
Charlie?
Charlie. Yep, resistance, R, divided by reactance, X, Rx, of either the inductance or capacitance, because they're both equal at resonance. What is the half-power bandwidth of a resonant circuit that has a resonant frequency of 7.1 megahertz and a Q of 150? Now, we did not work this one, but somebody tell me how to do it, and maybe do it on your calculator and give me the answer.
Charlie?
It is going to be Charlie. We're going to take 7.1 megahertz and divide it by 150, and we're going to come out with 47.3 kilohertz. Now, the two poll questions that are similar here are going to give us a frequency in megahertz and a Q, and the answer is always going to be in kilohertz, if that helps you. Just looking to see if I have any other tips to share here. Oh yeah, somebody else noticed that if you just divide the numbers, the significant digits will work out. So if you divide 71 by 150 or 7.1 divided by 150, you're going to come up with, the decimal point won't be in the right place, but the significant digits will. So that's another way you can get to this answer without having to think too hard. Here's another one. I think this is the one we did together.
I think we did the last one.
Oh, we did the last one. This one we didn't. Yep. But it works the same way. So somebody can either tell us how to do it or do it on your calculator quick and give us the answer.
Dave?
C
Charlie.
See Charlie, right.
Did somebody call me?
Nope. Go back to sleep.
Oh, thanks.
You're welcome. What is the effect of increasing Q in a series resonant circuit? If we increase the Q,
Charlie?
Charlie, internal voltages are going to increase, because increasing the Q is going to decrease the resistance, and the resistance is swamping out some of that reactance. All right. I think we're all done with calculations for this chapter, so I'm hoping we've got some smiling faces going on in our crew here. Components at microwave and RF and microwave frequencies. And skin effect. All right, so we've got three circles here. These Circles represent an end view of a piece of wire. So if you're wanting to jump start your car, you'd be using heavy-duty jumper cables made out of copper. And then the wire would look something like this. It'd probably be stranded rather than solid, but you'd be using every bit of that space. What happens at radio frequencies, though, the RF current tends to flow toward the outside of the wire. So here's a cross-sectional view of the same conductor, but notice how it's only the outside part that's being used. And here we've increased the frequency even further, and we wind up with a much smaller part of the wire being used. Now, you may have noticed for VHF and UHF antennas, they typically use aluminum tubing. It'd be a total waste of money to fill that tubing in with solid aluminum because the radio frequency wouldn't use it at all. So in terms of HF, up to, let's say, 30 megahertz, it's just the outer few thousandths of an inch that is carrying the RF current. With VHF and UHF, it's the outer few 10,000ths of an inch. So very, very little of that conductor is being used. It's only the outside edge. You can see why it's called skin effect, because it's the skin of the conductor that's really conducting the RF current. Now, with greater resistance in the circuit, since we're not using as much of the wire, it'll increase the resistance of the path. Q will be less. We're increasing the resistance, so Q would go down a little bit. So that's a reason why sometimes they'll silver plate inductors at these high frequencies, lower the resistance. So notice the blue text. We're going to consider skin effect in what are called the film capacitors. Now, what is a film capacitor? Well, it's two plates with some kind of a film in between. Think of it as a piece of plastic. So with rising RF, with rising radio frequency, skin depth decreases, becomes thinner. The conducting area decreases, driving up the component's resistance. Just like with the previous case we showed with tubular aluminum or wires. Skin effect is the primary cause of loss in film capacitors. We'll need to know. And there's a Wikipedia article if you want to dig deeper. Now, parasites. Well, parasites are unwanted capacitance or inductance. So I had to find a picture of a parasite. So here's a mosquito. That's a parasite. We don't want it. At VHF and above, parasitic effects become significant. So unwanted capacitance or inductance, where might that come from? Well, they're telling us to keep lead length short to minimize inductive reactance, because believe it or not, just a piece of wire has some inductance when it's carrying current. Keep lead length short to minimize inductive reactance at VHF and above. Short connections reduce phase shift at microwave frequencies. Remember the angles that we were calculating rather for impedance problems last week? Well, this is the same thing. As resistance increases, the phase angle will change, which is also phase shift. Short connections reduce phase shift at microwave frequencies. Well, where does it come from? Well, here's an inductor, and you can visualize that in between the turns of the inductor, there's going to be some capacitive effect, parasitic capacitance, or across the entire inductor, there's going to be some capacitance. So the inductor will have a nominal value, so the inductor might be rated at 10 millihenries, for example, or microhenries. But these capacitance effects are going to come in and change that overall picture. So interturn capacitance is the parasitic characteristic that creates an inductor's self-resonance. Self-resonance, well, what in the world are we talking about there? Well, remember when inductive and capacitive reactance were equal, were at resonance? Well, what happens here as frequency keeps increasing, at some point the inductive and capacitive reactance will become the same value, and the component will be self-resonant. And what happens when you continue to increase in frequency, the inductor will start acting like a capacitor. Very freaky, right? But it's true. We don't have to worry about that if we're using a commercially made radio, because the engineers that designed the radio have taken that into account. But you might have to do this if you're building your own equipment. So interturn capacitance is the parasitic characteristic that creates an inductor's self-resonance. Self-resonance results from the combination of a component's nominal and parasitic reactance. The nominal would be the value of the part, like it might be a 10 picofarad capacitor. But the leads on it have some inductance, and at some point they'll be equal. So self-resonance results from a combination of a component's nominal or rated value and the parasitic reactance, the reactance that you don't want or wish you didn't have. So let's look at self-resonance in a capacitor. So capacitor leads have some inductance, and quite often capacitors are wound. There's foils inside the capacitor with an insulating material. It's called a dielectric film here. And because this is built in a circular fashion, like a coil, there's going to be some inductance there. So capacitor leads have some inductance. Wound foil has some parasitic inductance, and you wind up with something that looks like this. You've got the lead inductance, you've got the nominal value of capacitance, and then you've got the internal winding of the capacitor, the way it's built. So self-resonance results from the combination of a component, and we've repeated this from the previous one. Self-resonance results from the combination of a component's nominal or stated value and the parasitic reactance that you get for free. All right, so that was the case of a film capacitor, just a capacitor in general. Now specifically, in electrolytic capacitors, the way they work, they actually use an oxide layer between the plates, extremely thin. Inductance from the turns of aluminum foil in an electrolytic capacitor cause them to be unsuitable at RF. So the self-resonant point for an electrolytic capacitor tends to be fairly low in frequency. So you'll only be using electrolytic capacitors for power supply filters and in audio circuits. You wouldn't be using them at RF. They wouldn't be suitable. A link here if you want to learn more. I'm really glad that the pool committee gives us a few really easy questions, and that's what these next couple are going to be like. So DIP stands for dual inline package, 2 rows of connecting pins on opposite side of the package. That's like this. You've seen integrated circuits that look like this. DIP is a through-hole device type. So you can see that there's actually holes in the circuit board. Before the soldering occurs, the part is pressed into the holes in the board and then soldered. The idea of pushing that component through the board, so it makes it a through-hole device. And these parts aren't used so commonly at UHF and higher because of the excessive lead lengths. Well, you might be looking at this and saying, well, this doesn't look like much of a lead length, but it does become significant. So how can we get rid of those lead lengths entirely? All right, more on lead lengths. So get rid of the leads. Well, that's what surface mount components do, or SMT, surface mount technology. So here we've got a picture of somebody's thumb, and these parts that look, we can actually see them. If you take one of these and put it on a thumbnail, it looks like a little bit bigger than a grain of sand. So because it is so small, you can get a lot of them in a smaller circuit area. You have shorter circuit board traces. The parts can be closer together, so you don't have to have long traces to go between the parts or foils on the circuit board. And components are going to have less parasitic inductance and capacitance because there's 3 different benefits here. We might be seeing on all of these coming our way. And then finally, SMT components have the least parasitic effects above the HF range. So your cell phone is full of these. Most modern electronics is full of these. In fact, if you are a kit builder, a lot of times if you order a kit, which means you have to put all the parts together yourself, a lot of times they will have pre-soldered all of the the SMT components for you, so you won't have to deal with those. Right on to some easy questions, I hope. What is the result of conductor skin effect?
Alpha.
Alpha resistance increases as the frequency increases because RF current flows closer to the surface. Why is it important to keep lead lengths short for components used in circuits for VHF and above?
Bravo.
Bravo. To minimize inductive reactance. Why are short connections used at microwave frequencies?
Bravo.
It is bravo. The parasitic reactances will cause phase shifts. What parasitic characteristic causes electrolytic capacitors to be unsuitable for use at RF?
Alpha.
It's,
No.
I'm not sure
Charlie.
I've heard that, but inductance, right, because the electrolytic capacitor is a foil wrapped around and around and around, which creates inductance. So that's why they're not good for RF frequencies. What parasitic characteristic creates an inductor's self-resonance? An inductor's self-resonance, resonance.
Delta.
Delta.
Yep, interturn capacitance. Absolutely right. What combines to create the self-resonance of a component?
Bravo.
Component's nominal or rated value and the parasitic reactance. It would be true for inductors or capacitors. What is the primary cause of loss in film capacitors at RF?
I remember this one.
No.
Delta.
Very good. Very good. Now see if you can remember it tomorrow. What,
Yeah.
Yeah, exactly. What of the which of the following device packages is a through-hole type?
Alpha.
Alpha.
Yeah, we only talked about one. These other component types are real things, but this is the only one we talked about, dual inline package. Which of the following component package types would have the least parasitic effects at frequencies above the HF range?
Delta.
Delta.
Surface mount, correct. What advantage does surface mount technology offer at RF compared to using through-hole components?
Delta.
Alpha.
Yep, that's all of those. Yep. What is a characteristic of dip packaging used for integrated circuits?
Delta.
Yeah, the distractors are pretty interesting because they could all be abbreviated DIP, but D is correct. 2 rows of connecting pins placed on opposite sides of the package. Why are dip through-hole package ICs not typically used at UHF and higher?
Charlie.
Charlie. See, I told you that we had some interesting, easy questions. Okay, this would be a perfect time for a break. We've been going at it for about an hour. We're going to come back after the break and talk about magnetic cores. And then when we get through that, I'll have a demo for you that I think you'll see will reinforce some of the things we talk about. So go ahead and take a break, do something different, walk around, get a drink of water, which I'm going to do, and we'll see you in 5. Minnesota, and we're ready for round 2 here after the intermission. So we're going to talk about magnetic cores. This is the last section that we have in the chapter, and then we'll move on to a demo after that. This is a fairly easy section as well, so more good news. Let your brains cool off a little bit. So what are magnetic cores? Well, these are things associated with inductors or coils. Inductors store magnetic energy, creating reactance. So the number of turns on a coil affect its inductance. The more turns, the higher the inductance. And the core material, you can put a certain kind of material inside the coil and change its inductance. And there's a couple of different kinds of material. We've got what's called air, and I'll show you, get this turned back on again. This is what would be considered an air inductor. There we go. So the inside of the coil is just air. They've got plastic pieces that are glued to the coil to hold it in place. Now, a magnetic material will increase the storage of energy and the inductance. Remember, we said that in a coil or in an inductor, a magnetic field builds up around the component when current is flowing through it. Well, if we can add something to the core of the inductor, that potentially could increase the inductance as well by focusing that magnetic energy. So magnetic material increases the storage of energy and the inductance. And there's a couple that we'll talk about. Ferrite, which is a ceramic mixture with components of a ferric or iron-based material. And ferrite generally requires fewer turns to produce a given inductance and value. So ferrite inserted into a coil will increase the inductance. Now, a big fancy word, permeability is the core material property that determines the inductance of an inductor, or how much that inductance is going to increase when it becomes present. And there's different kinds of core material. Now, air is the reference. So an air-wound coil, as shown here, is defined as having a permeability of 1. Now, powdered iron and ferrite have a permeability that's greater than 1. So when we insert that kind of material into the inductor, the inductance will go up. Now, brass is the oddball. Brass as a material has a permeability of less than 1, so it'll decrease inductance when inserted into a coil. And this is a real thing. I remember from my two-way radio days that we had both brass and ferrite slugs in coils we had to tune. Here's some pictures. Now, there's different shapes, and they have different properties. So the core material will be effective over a certain range of frequencies. So there's different formulations of ferrite material used for different frequencies. Powdered iron versus ferrite material. Well, powdered iron, and iron is ferric as well, but we're talking basically powders here, and powdered iron is just that. Powdered iron performs better than ferrite at high current. I'll have a diagram of that coming up. Core shape is important. There's a couple of different shapes. There's a straight shape, and I'll show you, like this one here is called the solenoidal shape, and this one here is called a toroid or donut. Easy way to remember it. So magnetic field of one inductor can interact with nearby components. That's sometimes a bad thing, because you don't want these parts conveying RF energy into other parts. In the two pictures, I'm showing some different kinds of inductors here. And this is a picture of a low-pass filter board for a 1500 watt amplifier. You can see that the toroids are fairly closely spaced together. These are all relays that'll switch in different numbers of toroids. So magnetic field of one inductor can interact with another one. Can be good or bad. Toroids reduce unwanted coupling by keeping most of the magnetic field contained within the core material or inside the donut. Now you might be wondering, why could it be a good thing? Well, maybe you want to couple energy from this circuit over to an adjacent circuit, like as in a transformer. In that case, you might want to line two solenoidal inductors end to end so that you can get some coupling between them on purpose. But generally, when they install these, or most designers will put them perpendicular to each other so they won't interact. Ferrite beads. You've seen these. Maybe you didn't know what they were all about, but on some of your power cords at home, you've got one of these blobby things on the end, usually on the equipment side, some on the power AC power side, or sometimes both. So this is a ferrite element, or ferrite bead. And here's a couple of others that you've probably seen. This is a snap-on ferrite, where you can put it onto a wire that already has connectors on it. It's all different ways of doing it. So a ferrite bead is a small core slipped over component leads. And the way the pool wants us to remember this, commonly used at VHF and UHF as parasitic suppressors at the input and output terminals of a transistor HF amplifier. Well, they'll actually work on just about any kind of a signal, but they've specifically given one example here in the pool. Another thing that's useful to know, each time the wire passes through the core of a toroid, it counts as one turn. So just taking something that's like here's one here, a toroid, and we've passed the wire through it twice. That's a two-turn toroid. One turn is you just poke the wire through it one time without wrapping it around at all. There's the two-turn case. Some more pictures down here. The reason this might be important is because if you're building a kit, it's fairly common for the instructions in the kit to have you wind your own toroids, so it's important to know how to count the turns. More on magnetic cores. You might have seen some of these funny looking things in radios if you've peeked inside. In this case, we've got, these all appear to be tunable. There's some kind of a ferrite slug inside that you would adjust with a special tuning tool. Just different kinds you might see. Sometimes magnetic material will be threaded into a paper or plastic core to make the inductor variable. So if you could picture a soda straw and a round threaded piece of ferrite material, you could screw that down into the inside of the soda straw. Well, they don't use soda straws, but that's the concept of how it works. Ferrite material will increase the inductance as it goes into the coil form, and brass will reduce the inductance, as we saw. Okay, toroids resemble the donut. I don't think you'd want to eat one or put frosting on one. Primary advantage of a toroidal core over a solenoidal core. This would be an example of a solenoid. It's straight solenoidal core. Primary advantage of a toroidal core over a solenoidal core. Toroidal cores confine most of the magnetic energy within the core material, so they tend not to couple energy to other circuit elements near them. Less coupling to nearby components, more inductance per turn. So you get a higher value of inductance by using a toroid. And temperature stability is another consideration. So powdered iron versus ferrite material, powdered iron has the highest temperature stability of its magnetic characteristics. If you've got a circuit that's running a fair amount of current and the inductor is going to be getting hot, powdered iron would be preferable. We're talking RF frequencies here. So what are the potential problems? I mentioned I'd be showing a graph. I'll get to that in a second. Inductor saturation is caused by operation at excessive magnetic flux, which would mean excessive current through the part. Excessive current ability of the inductor's core to store magnetic energy has been exceeded. And you'd wind up with a graph like this. Its response would become nonlinear. You want to pick a part that would operate over the linear range to avoid this issue. A saturated inductor will behave in a nonlinear fashion, excuse me, possibly causing harmonics and distortion. And then we've got transformers. These are generally low frequency, like it's 120 volts in and then whatever value coming out. So power transformers are also inductors. And an interesting effect that happens here, because they're such low frequencies, a lot of times there's heavy iron to help with the coupling between the primary and the secondary sides of the transformer. But some of that, a result of that style of construction is that a certain amount of current is induced into the core material. Because you can see that this core is like a one-turn coil, which is shorted out, right? So it's going to be absorbing some current just by the fact that it's a big hunk of iron there. That's called an eddy current. I don't know how Eddie got to get into that thing there, but there he is. There's Eddie. Eddy currents cause wasted energy in the form of heat. Cores of inductors, and I'll have a picture of this if it'll show up on our camera. Cores of inductors and transformers are sometimes constructed of thin layers. You can kind of see that here, to reduce power loss from eddy currents in the core. In fact, if you take one of these apart, and I don't know why I was so interested in this in my younger days, but I actually took some transformers apart. And yeah, you can actually peel these things apart. They quite often have these pieces stuck together with varnish to help insulate the pieces from one another and to keep them from buzzing. But common construction there, just a couple different views. Now there's an effect called magnetizing current that you only see that term associated with power transformers and sometimes motor windings. So, and this is the impact. Current in the primary winding of a transformer with no load attached to the secondary is called magnetizing current. So you'd think if there wasn't anything attached to the secondary of a transformer, there would be no current flowing whatsoever. Well, there is a little bit, and that's called magnetizing current. Kind of an oddball question, because we've been dealing with all RF, and this has to do with 60 cycle, primarily, power circuits. And on to some questions, which will wrap up the technical part of the chapter. Why are the cores of inductors and transformers sometimes constructed of thin layers?
Beta.
Yep. To reduce power loss from eddy currents in the core. Bravo. How do ferrite and powdered iron how do ferrite and powdered iron compare for use as an inductor core?
Charlie?
Yeah, it is Charlie. Ferrite cores generally require fewer turns to produce a given inductance value. What core material property determines the inductance of an inductor?
E.
Yep, delta, permeability, big fancy word. What is the current that flows in the primary winding of a transformer when there is no load on the secondary winding?
Delta.
Delta.
Magnetizing current.
Correct, yep. Yeah, see, I told you that this was a lot easier, so thank you, no calculations. Which of the following materials has the highest temperature stability of its magnetic characteristics?
Beta.
Bravo?
Bravo, powdered iron. What devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of a transistor HF amplifier?
Charlie.
Charlie?
That's
Charlie.
ferrite beads. And ferrites are your friends. Do you want to tell us about your second floor ham shack, Gary?
Well, I used to have a ham shack on the second floor of my old residence, and so grounding was very difficult, if not impossible. And so I would pick up stray RF from every transmission I would make. So I had to take all of the cables I had up there and wrap them through or around ferrites to minimize the stray RF pickup. So absolutely, ferrites are your friend.
Yes. And I had a case, I had a keyboard on my computer, and when I would transmit, the keyboard was non-responsive. And I fixed that by winding the keyboard. It was a wired keyboard, and I wrapped both the keyboard side and the computer side a bunch of times around some large ferrites, and that fixed the problem for me. So ferrites are your friend. What is a primary advantage of using a toroidal core instead of a solenoidal core in an inductor?
Alpha.
Alpha.
Correct. Toroidal cores confine most of the magnetic energy field within the core material. Which type of material decreases inductance when inserted into a coil?
Bravo.
Bravo, very good. Brass. What causes inductor saturation?
Bravo. Bravo.
Well, it's actually Charlie.
Charlie.
Operation at excessive magnetic flux, and that happens if you're passing more current through the device than it's rated for.
Too much power.
Too much power. Yep. Now, flip this up again, formula review. I don't know if I mentioned every one of these as we came across them tonight, but if you've been trying to write those down as we went through the presentation and you missed any of them, they're on the extra class reference sheet. And what I'd like for you to try to do is to fill this out and then try to reproduce it from memory tomorrow, maybe a couple times in the week to come. Then you'll have all of the formulas relating to calculations you might need to make for the exam if you use the calculator method of getting to the answers. Guess what? That wraps up Chapter 4. We still have a demonstration to do after this, but hopefully you're breathing a big sigh of relief right now. We got through Chapter 4. Yay. Okay. So this is all of you, I hope, all happy and jumping up and down. Of course, the hard part is yet to come. That's the review and the practice, and you need to do that so that you own this material. So if you've followed with us so far, you've got a great chance of getting all of the pool questions from this chapter right. There's probably only going to be a maximum of 2 calculation questions on your exam. Could even be none. So the exam review tool will now work for the entire chapter. Since you've been through both halves of the chapter, you can go and chase after that. I don't think I mentioned or didn't elaborate on one of the handouts that I provided in my Thursday mailing. I'll just give you a picture of it quick. It says extra class calculation questions. From Chapter 4. There's only 12, believe it or not. And the approach that it took here was to present the question. Like the first one is E5A11, and spell that out. And then I provide a solution tip for each one of these questions. This one says megahertz divided by Q, or the bigger number divided by the smaller. Answer 47.3 kilohertz. Now, why would this be useful? Well, if you're doing an online test and they will only allow you to use the calculator on your computer or perhaps a 4-function calculator, you'd be able to solve this without using the TI-36X Pro. And I've taken the same approach for all 12 questions, and in the solution tips, if there's a shortcut, I share it. And there's just 3 cases where I couldn't come up with a shortcut, so I came up with a memorization table. Let's see if I can find that in my list here. Yeah, here it is. These were the 3 phase angle problems. And if you can associate the capacitive reactance with the phase angle, if you can just memorize these, the values for these 3 problems, you'll be able to answer those without a calculator. And they'll ask you also if current or voltage is leading or lagging, but you know how to do that from Eli the Iceman. But the phase angle, that's hard to figure out without a calculator. So there's only 3 out of this group of 12 where you actually have to memorize something if you want to be able to do it without a calculator, with just a 4-function calculator. So I think that this will give you a path to get through all of these, should you need it. So what I want to do next is set up a demo here. Get rid of the calculator, get rid of our magic sheet. And the first thing I'm going to show you, get this centered and placed for us here. Zoom out the other way. Now what this is an LCR meter, meaning inductance, capacitance, and resistance. This is a DEREE, or DE 5000. These are about $100. They, the reason that you might want to consider some kind of an LCR meter, not necessarily this one, this is a little bit fancier one. If you're doing a kit building, then sometimes it's helpful to be able to measure the components to make sure that they are what you think they are. What I've done here, I've connected an air-wound inductor to the LCR meter. I'm going to turn it on. Let it wake up. It's a little bit hard to read here, but it says that it's measuring a value of 41.6 microhenries. That seems like a pretty small inductance value, but you'll see these kinds of components in the final amplifier stages of transmitters or in high-powered amplifiers frequently. And what I wanted to prove to you is that inserting a ferrite material into the coil will indeed raise the value of the inductance. So what I have here is a hunk of ferrite material, and I'm going to put it part way into the coil. You'll see that we're now at 54.8 microhenries. When we didn't have it in there at all, 41.6. So here's about halfway in. It went up to 56.9. If I push it all the way in and let it settle, we're up to 75. So I've just proved to you that if you put a ferric material into a coil, it will raise the inductance. I'm sure you believe me anyway, but it's just kind of fun to see that. The next thing I want to show you is what happens with a variable capacitor. So I'll disconnect this. And here we have a variable capacitor. You see it's a bunch of plates here. And if I put a tuning tool in this end, as I turn it, you'll see that we're opening and closing the plates as they mesh with each other. So I'll open it up about halfway, and we'll hook up our meter to it. Let's see, I've got two clip leads. I need to use the other one here as well. Otherwise you won't be able to see the display at the same time. All right, still connecting. Okay, so I've got the capacitor about halfway open right now, and it's reading 52, 53 picofarads. As I'm moving my hand around, I'm probably changing the capacitance a little bit. But let me fully mesh the plates. Fully mesh the plates. See what happens. Okay, now we're at 93-ish picofarads. Let me completely open them. Now we're at about 27, well, 15 picofarads as it's settling down. So you can see that this stuff actually works. The next thing that I want to show you is pretty interesting. I have here an inductor. You notice there's only two leads coming off of it. So this is something that would be used probably in a power supply for filtering. I'm hoping it's a little there. I think you can see it. See all of those you can see all of the individual, this is made up of a whole bunch of little pieces of the steel, just like we showed. Now this is fairly heavy, so there's going to be a lot of wire wound around this thing. So we've been looking at things in the microhenry range. Let's see what we've got here.
Zoom out.
I will in a second. And hook up the clip leads to it. And zoom out. And this is kind of amazing to me. It says 5.6 henries. It's a huge amount of inductance. Again, used for power supply filtering. And remember how Gary and I both shared stories, I think last week, about getting knocked on our rear end from a low voltage source being hooked up to an inductor?
Back EMF.
I think I can demonstrate that here. First thing I'm going to do is unhook this. I'm going to set the meter aside and replace it with a battery. Here's a battery by NEO Power. And this has got an internal winding that's in the neighborhood of 300 to 500 ohms. So first thing I'm going to do is take a resistor. This is a 330 ohm resistor, approximately matching the internal resistance of our coil. And I'm going to hook a battery. This is a 13.8 volt battery across it. And you're not going to see anything happening yet. This will get a little bit warm. But what I want to show you is what happens when I disconnect it. I'm going to turn the camera light off so you can see it better. Okay, you can still see it. Now, if I disconnect the resistor, you would expect that nothing would happen, and it doesn't, okay? You don't see any arcing or sparking or anything like that. Nothing's going on. So let me hook this humongous inductor up. Trying to get the clip lead hooked on. There we go. All right, so what I've done here is hook the battery up to the inductor, and I want to show you what happens when I disconnect the battery. I hope this will show up. So,
We saw it.
okay, as I'm touching it, you'll see a spark exists when I disconnect. I'm being very careful not to touch this. I think you can see them happening occasionally when I get it in just the right spot. Pretty good arc happening there. Well, that's perhaps hundreds or even thousands of volts happening there. Remember when we talked about current flowing through an inductor? And when you disconnect, when you take away the battery, that magnetic field collapses instantly. That's what we're seeing. That's what that spark is. It's the magnetic field collapsing as the voltage is taken away. So I thought that would be a very interesting demo as well. So at this point, I think that's all that I had to show you. Hopefully we've reinforced some of the things we talked about and proved that they're real. And at this point, we'll move on to class chat. We're about 20 minutes early, so we've got plenty of time for any questions that people may have.
Let me take off the spotlight here.
All right. Yeah, Gary's jumping around between operating positions back there because it's just him there doing the work of two people tonight.
Questions, comments?
Yes. So you don't have...
I'm surprised you don't have a Jacob ladder.
Say that your audio is real low. Say
I don't
again.
have a Jacob's ladder in the studio. One of
Oh.
those science fiction-like things
okay.
that the lightning goes up and down.
Yeah.
Or a small Tesla coil.
Yeah, that would be fun. Then if I make a mistake, somebody can zap me with it, maybe.
There you
I was starting to ask, and I'm not sure I know how to ask the question well, but skin effect, and we talked about solid wire, we talked about tubing, and there was something in there about resistance increasing, and I wasn't sure how that was working. I would have thought that resistance would be decreasing around the outside of the conductor.
Okay, well, let me try one approach, and Gary might have another idea. A wire, as it gets thinner and thinner, will be becoming a higher and higher resistance. So a number 6 wire, for example, like you might be using in your grounding system, would have very low resistance. A number 22 wire would have much higher resistance because there's less circular area in the wire. And what happens with skin effect, you get the effect of having a skinnier and skinnier wire because you're using much less of the wire to conduct current. So that's the first pass at an answer. I don't know if that helps you, though.
Well, and the other thing we were talking about, as you go up in frequency, the amount of the metal that it's using on the surface to carry the current gets thinner and thinner, which is why they'll silver plate VHF and UHF inductors and things like that in order to have the lowest possible resistance at that very outer edge at VHF and UHF for the currents there.
Yep.
Thank you.
All right. Any other questions or comments? Do y'all think that you might be able to get through Chapter 4 now? And you'll find out when you go through the self-test. But yeah, we shared every tip we could think of. The hard way to do it, the easy way to do it, the shortcuts, analogies. Yeah, we tried our best to help you through it. And a big part of that was avoiding all of the stuff that we didn't actually need in the book, which there's a lot of.
Thank you.
Yep, you bet.
Well, I'm proud of you all, but we're not done because next week, Chapter 5, it's another meaty chapter, building blocks and components. We're going to talk about a lot of different things, the entire chapter in the 2-hour session. So take some time this weekend, pace yourself, and make sure you get a chance to read through Chapter 5 in the book.
Right. Yep, and keep reviewing the stuff that you've already learned too to make it to plug your memory leaks. Yep. All right. Well,
Alrighty, y'all.
With that, we'll close.
Thank you all.
Thank you very much.
Thanks for being with us, and 73.
73.
You bet.
Thank you all.